Welcome back to Calculus. We're going to talk a little bit more of Math 122, and this time 2.6, higher order derivatives. One caution, however, you must be fluent in everything up through 2.4. That's the product and quotient rules. If you're struggling with the chain rule, that's fine. That takes a while to really get decent working. But if you're not familiar enough with up through the product and quotient rules, go back. Get the practice you need. That said, let's move forward. Higher order derivatives in 2.6 is actually, compared to the chain rule, it's almost like comic relief. It is that easy, if you've gotten here and you've had sufficient practice. So let's take a look at higher order derivatives. That's all we're going to do in this section. And we're going to use the position and velocity and acceleration concepts, but it's all about higher order derivatives. So let's get started. It's very easy. I can tell you in 1 minute enough that you can probably take off and work all the problems you need to, or work examples in your field. So here we go. The standard derivative, we've been working with this for several weeks now. And let's see, where's my pen? There's my pen, okay. So we've been calling functions f of x, and we've taken that function and we found the first derivative. That's the first derivative. With that mark up there, we also call it dy dx, and a couple of other things like maybe y prime, for example. Now the derivative of that, okay, you've taken the derivative, you've gone from here to there. What we're going to do in this one is go from there to the derivative of the derivative. There we go, like that. Well, it's not too hard, really. Imagine this. Let's say our function is, let's start with something really simple, x to the 6th. Maybe we should throw something out here in front. Let's say this is 5x to the 6th. Can you find the derivative of this in, say, 5 seconds? If you do, you're maybe in good shape. F prime of x. The first derivative is what we'll call it now. Bring that 6 out front. You get a 30 for a coefficient. The 6 out here becomes 6 minus 1, or 5. And the first derivative, notice there's one mark up here, one accent mark, is 30x to the 5th. Now what about taking the derivative of this? Well, we put 2 marks up there now because we've taken the derivative twice. We'll take that 5, move it out front. 5 times 30 is 150, and the x becomes x to the 4th. There's the second derivative. That's all you really need to know. Isn't that surprising? You could even take the third derivative. Not terrible. Third derivative, just take the one above, bring that 4 out front. That's 600. X to the what? X to the 3rd. There you go. Let's take it one step further. X to the 4th derivative. That's no big deal either. Bring that 3 out front. You've got 1800 x to the 2nd power. There you go. Now, notice those accent marks, they're getting a bit much. So another way of writing this so we don't lose track of how many marks we've got is we can put a 4 up there in the superscript place, and that'll represent 4 of those asterisks or apostrophes. In general, it would look like this. That's the nth derivative of x. Okay, that's it. We're going to go through a few other things, but that's the basic lesson right there. We're going to look at some examples though, like the distance function, velocity function, acceleration function. See how they fit in. Oops. Let me clear that so it doesn't look like a piece of junk to you. Erasing. There we go. Okay, there's the second derivative. Third derivative, 3 accent marks, 3 apostrophes. You can continue that process as far as you need to and get higher order derivatives. And that's what they look like. Notice somewhere around 4, you decide, I'm losing track of how many apostrophes there are up there. And if you're not careful, some of them could get mixed in with others. You don't want that to happen. So we use a superscript up here. That's where the power usually is. But we put it in parentheses so we don't think it's y to the 4th power. It's the 4th derivative of y instead. All right, let's get to an example. Notice we want the 3rd derivative and we want it evaluated at 2. So how do we start? Well, we're going to differentiate 3 times first. Forget the 2. Hear me? Forget the 2. You have to find the derivatives first and then you put in the 2. So here's your first derivative. Could you do that? Quickly. It has to be quickly. We don't want to spend all day getting the derivative of just the first term, or the second, or the third. They should be flying out of your pen. There's the first derivative, second derivative, and the derivative of that is the 3rd derivative. There you go. Now it's time to put the 2 in. Put the 2 in there. And the 3rd derivative at 2 is negative 36. Notice, especially, the degree of the polynomial drops by 1 every time you take the derivative. Well, that's not a surprise, right? You're subtracting 1 from the exponent each time. Now remember, it's not always so nice as subtracting 5 minus 1 and getting a 4. Sometimes you might have fractions. A little bit of exercise of your fraction skills sometimes. I'm sorry, fractions are numbers also. Eventually, if you take enough derivatives, you end up with a constant function. So if I take f of x, for example, and we'll just make this generic for the time being. And if I take enough of these derivatives, I eventually end up with a constant. For example, it might end up being a 52, or a 7, or a negative 8. But eventually, you end up with a constant if you take enough higher order derivatives. So here's the general look. Here's a polynomial, one of the nice ones. If you take the nth order derivative of one that has x to the n, you end up with a constant. This is a constant. Notice there's no x's there. If you want a shortcut, which you really don't need, but if you did, that coefficient or one of the factors of the nth order derivative would be n factorial. That's 1 times 2 times 3 all the way up to n. And then times this a to the n, which is the number you had up here. So the factorial of n times this first coefficient is the constant you end up with. Everything higher than that, derivative-wise, is 0, period. Because, why? Because the derivative of a constant is 0. Remember? If g of x equals, let's make this exotic while we're doing it. Let's suppose it's pi. What's the derivative of g of x? Because this is a constant, it's 0. First four derivatives of y to the negative 1. Remember, it's y equals 1 over x. Remember our rewriting that's so helpful? So there was your original function. There's your first derivative. There's your second derivative, your third derivative, and your fourth derivative. Now we're going to talk about a little bit of application, and we're going to talk about acceleration. If you remember, we talked about the distance function. For some reason, s represents distance. I'm guessing this might be from some other language, and I don't know what that is, but s probably means distance in some language. If I had to guess, I might say maybe German. If you find out, let me know. It'd be a curiosity. With that distance function, the first derivative, remember, we've done this, is the velocity function. And acceleration, as it turns out, if we take the derivative of the velocity function, we get the acceleration function. And keep in mind that that would be the second derivative of the distance function. All this blends in together, works really well together. Now, free-falling object, what are we talking about? Let's suppose we've got a cliff here. I'm not very good at drawing, but here you are at the top of a cliff. And let's not say you jump off of it. Let's suppose you throw a rock off the cliff. So it ends up being here and here and here, and eventually hitting the bottom. The rate of change of the position, that's distance, where it is with respect to a certain place, whatever you call ground zero, for example. The rate of change of the position with respect to time is called velocity. In other words, s prime of t equals velocity with respect to time. Similarly, if we take v prime, we end up with a function of acceleration of that object as it's falling. So acceleration, here's the position function. One more time. Now I might be a little bit picky here, and I might say that position function is a function of time, because where it falls in that free fall example depends on, this says where it is, and this says at what time we're interested in. It's a position function. If we take the derivative, also known as s prime of t, we get the first derivative, or the velocity function. If we take the derivative of that, and here's another form of that, s double prime of t, which is the velocity derivative, all that goes together. So at any particular time, you can put the value of t in, and you can find the position, or the velocity, or the acceleration. So here's the example. Oh, much better than my picture, right? So this guy, this is you, and you're at the top of a cliff. You were looking out at the ocean or a river, and you decide, I'm going to throw a rock up in the air. And notice you're 160 feet above that water down here. You're going to throw it upward at 48 feet per second. Notice that this is a positive 48. That's why we say it's upward. This is the position function. Now this is a shortened version of, first of all, remember it's a function, so it's a position function with respect to time. And here on Earth, which is where we are, we've got 1/2 gt squared plus v0t plus s0. Okay, what does all that mean? And what's the connection between these two? First of all, this g represents the acceleration due to gravity. And g, typically on the surface of the Earth, is minus 32 feet per second squared. Notice that if you put a minus 32 in where the g is, you get minus 16. That's where the minus 16 comes from. This v sub 0 means how fast was the rock going at time 0. Well, it started out at 48 feet per second. Up. Positive. Positive means it was going upward to begin with. And this S0 means where was the rock when you let go of it? Well, it was 160 feet above the water. You threw it from here, it went upward for a while, and of course you know what gravity does, pulls it back down. So there's your position function and what the pieces represent. Acceleration is in here, the initial velocity is here, and the initial position is here. Now what you want to do is find the height and acceleration of the ball at t equals 3 seconds. So you let the ball go at t equals 0 seconds. Where is the ball 3 seconds later? Is it still up in the air above you, or is it somewhere down here? Let's see. So first of all, you're going to take that position function and differentiate that to get the velocity, and then you'll take the derivative of that one to get the acceleration function. So there's our velocity function. Could you do this real fast? I hope so. Bring that 2 out front, negative 32. T squared becomes t, and so on. 48t, 48. Should be real easy. 160, 0. That's a constant, so the derivative of that is 0. Excuse me. Differentiating the velocity function, we get the acceleration function. Now what do we have? We've got the position function, the velocity function, and we've got the acceleration function. And we're interested in what's going on the 3 seconds. 3 seconds after you let go of the ball, you've thrown it in the air, just let go of it. 3 seconds later, where is it? What's it doing? And what's the acceleration of that thing? So for the height, remember, this is position at time 0. This is an S, not a 5. Just put the 3 in the position function, and you can evaluate that very easily. You should be able to do it by hand too. You shouldn't need to depend on your calculator all the time. So it's 160 feet. Well, that makes sense. You're 160 feet above that river or ocean, whatever it was. So that's where it should be at the moment, at the split second that you let go of the ball. How about the velocity? We'll take that velocity function up here, put in 3 for the t in the velocity function, and evaluate it. That's how fast your rock is moving 3 seconds after you let it go. By the way, notice when you let it go, it was going 48 feet per second up. 3 seconds later, it's going 48 feet per second down. This means down. How about acceleration? Well, that's pretty easy. There is no t involved here. The acceleration is negative 32 feet per second squared, period. That's it. So g is the acceleration due to gravity. That's what physicists use, and I know that because I taught physics. Note that it's negative. That means the ball is being pulled down toward the earth. Negative 32 feet per second squared. I got a little bit carried away there. Okay. That's on the surface of the earth. What about the moon? We're not always on the surface of the earth. Well, I guess we are. But we can think about being on the surface of the moon. What about that? Well, the acceleration due to gravity is not the same on the moon because the moon doesn't have as much mass. So it doesn't pull things toward its center quite as strongly as the earth does. Notice you got almost the same situation here. You still got S of t, but this one's for the moon, but it's still negative g t 1/2 gt squared plus initial velocity times time plus the initial height. Now I use h sub 0, but if we're using s for position, then s sub 0 makes more sense really. And this works for all objects. It doesn't matter whether it's a hammer or a feather. It still works the same. What we're ignoring is the air resistance, things like that. We're just making it a very, very simple thing. Here's another one, a velocity function. Remember, that's s prime of t for this automobile. And when we took that, we got our velocity function, 80t over t plus 5. Find the velocity. Well, that should be pretty easy. We've already got that function at 10-second intervals from t equals 0 to t equals 60. Well, for the velocity, all you're going to have to do is put 0 in here and put 10 in there, 20, 30, 40, 50, and then 60 to get the various speeds at those times. And then to get the acceleration, we're going to take the derivative of this thing and then put in 0, 10, 20, 30, 40, 50, 60 in the acceleration function to get our values. So here's our acceleration function. And unfortunately, we had to use the quotient rule, but by this time, it shouldn't be too hard for you. You should know you start with the function that's on the bottom, derivative of the top, quotient function, you have a minus there, and then you switch the two roles. This is the function on the top, and this is the derivative of what was on the bottom. And on the bottom, the new bottom for the quotient rule, you have the square of the original denominator. If you need to, take a look back there at our velocity function, and there we go. There's the derivative of that velocity function for the automobile. A little bit of cleanup or simplification there. And then we'll put our values in. Here are the values of t we were interested in. 0 seconds and at 10-second intervals, up through 60. There's our original velocity function. All we need to do to get those values is put the t in for the velocity function, 0, 10, 20, and so on, and evaluate for those particular values of t. Notice we're getting pretty close to 73, 74, somewhere around there. Here's the acceleration function. Just put these values of t in the acceleration function and get our values for the acceleration. Notice the acceleration is easing off. If you think about riding in an automobile, when it starts up, that's at time 0, you can feel that acceleration. But as you get closer and closer to 60, you don't have as much acceleration. It doesn't push you back into the chair or the cushion as much. In other words, you feel changes in velocity. You don't feel the velocity. If you're only going 60 miles an hour and you don't change it, it feels like you're going 0, really. You feel the changes in velocity. You feel the acceleration, but you don't feel the velocity. Well, that's it for higher order derivatives. I hope you've accepted some of that and enjoyed a little bit of it, perhaps. Well, next time, we're going to attack something a little bit different. We're going to talk about implicit differentiation. So make sure you've got your basics down. If you've taken a few days off, get some practice again, especially with that chain rule, because we'll need to use that constantly. And I'll see you in implicit differentiation, which is in section 2.7. Here's a short review of what you just learned.
Hi, my name is Ava, and today's topic is higher order derivatives. Now, because the derivative of a function y equals f of x is itself a function y prime equals f prime of x, you can take the derivative of f prime of x, which is generally referred to as the second derivative of f of x, and write it as the second derivative of f of x, or f squared. This differentiation process can be continued to find the third, fourth, and successive derivatives of f of x, which are called the higher order derivatives of f of x. Because the prime notation for derivatives would eventually become somewhat messy, it is preferable to put the number of the derivative as an exponent to the right of the y. Example 1. Find the first, second, and third derivatives of f of x equals 5x to the power of 4 minus 3x to the power of 3 plus 7x to the power of 2 minus what? Minus 9x plus 2. The first derivative would be 20x to the power of 3 minus 9x to the power of 2 plus 14x minus 9. The second derivative would be equal to f squared equals 60x squared minus 18x plus 14. The third derivative would be equal to f cubed equals 120x minus 18.